All right, so as Richard said, the title of this presentation is Closing in on NIST, because that's what we are in the process of doing or trying to do. And we're going to be focusing on NIST's response to the request for correction that we submitted earlier this year. And there is a little subtitle to go along with that, which is a new standard for evasiveness. That's actually a reference to a presentation that Kevin Ryan gave back in 2006 on the NIST report on the Twin Towers, which was called a new standard for deception. And so now in NIST's response to our request for correction, NIST is setting a new standard for evasiveness along with deception. So that's what we'll be talking about. And as on the right, there is the first page of the request for correction. So along with AE 911 Truth, there were several other requesters involved in submitting this request. In order to request a correction to information that's disseminated by a federal agency, you have to be affected by that information somehow. And so one of the categories of requesters involved were 9/11 family members. The folks who are signed on to the request their names are there on the left, and their deceased loved ones are shown on the right. And so I just wanted to take a moment to recognize and thank all of those family members, and their loved ones are Jeff Campbell, Gene DePalma, William Krukowski, Thomas Hetzel, Bobby McIlvain, and Edward Papa. So thank you all for being a part of this effort. The other category of requesters we have are other architects and structural engineers, almost all of whom have signed AE 911 Truth's petition, but are also practicing architects and structural engineers on their own, who are also affected by the information that NIST disseminated in its final report on the collapse of World Trade Center Building 7. So in total, we had 88 architects and structural engineers who joined this request. And thank you all as well. The background to the request is that, as many viewers will know, Architects and Engineers for 9/11 Truth for several years was involved in funding and overseeing a study by Professor Leroy Halsey at the University of Alaska Fairbanks. And the final report of that study was issued in March. And along the way, as the findings of the study started to become clear, we realized that one of the ways that this study could be very useful in the future would be to submit a request for correction, relying on or citing the study and the findings of the study in large part. And so that's what the request does. As we'll show in a fair amount of detail shortly, 4 or 5 of the key points in the request for correction are really substantiated by the findings in the UAF report. And so just want to thank Dr. Halsey and Dr. Kwan and Dr. Shao for their work over these past 4 or 5 years. The goal of the request, just to put it very simply, quoting one sentence from the request, the only way that each of these information quality violations can ultimately be addressed is for NIST to develop a new probable collapse sequence that is both physically possible and consistent with the data presented herein. So what we are essentially trying to do is highlight several areas of the NIST report where the information that is disseminated is not compliant with their information quality standards, and in order to comply with those standards, they need to discard their probable collapse sequence, or essentially their theory, and develop a new one. And as you'll see, as Tony and I will explain, their theory is both physically impossible. It's physically impossible based on the features of the building and how the features of the building would behave, and it's also inconsistent with all of the other evidence that we have about how the building came down. So before I hand it off to Mick to talk a little bit more about the Data Quality Act and his role in this whole effort, I'm going to play the video of Building 7 coming down for anybody who has not seen it before. So it's about 23 seconds. And I want, before you watch it, I want to also say, focus a lot on the East Penthouse, which is the structure that comes down first. It's in the top left-hand side of the building in this video. A lot of the discussion and critique of the NIST report and a lot of the the things that NIST claims in its report have a lot to do with why did that penthouse come down first, and how did the collapse of that penthouse and the columns that allegedly failed under that penthouse low down in the building initiate a progressive collapse of the entire structure. So keep an eye out for that. All right. All right, Mick, why don't you tell us about the Data Quality Act? Right now, well, 1 second. Right now, I think Mick is muted. Richard.
Not anymore. Right. Sorry. So I appreciate the opportunity to join you all. And let me thank AE while I have the opportunity publicly for doing this request for correction, which I've been very impressed with. My role has been to advise Ted, Richard, Tony, and the folks at AE on the legal ins and outs of the Data Quality Act to sort of set the stage for what we hope will not be needed, which is a lawsuit. At the moment, we're in the stage where NIST has denied a very well put together request for correction by AE at the initial decision stage. And we're looking at an administrative appeal due, and Ted will correct me, but I think this month on the 27th. And that will not go to a court yet. That goes to a higher level at NIST. And if the agency again rejects AE's arguments that the Building 7 study violated the Data Quality Act, at that point, we're looking at a federal court litigation. The Data Quality Act does require certain things of NIST, and AE has done a remarkable job of articulating clearly, notwithstanding technical complexities, the violations by NIST of the Data Quality Act. NIST is obligated to use data that's reliable, accurate, unbiased. They're required to use data that's reproducible, that's transparent. There are some technical definitions about what those terms mean, but what we've gotten from NIST so far, and you'll hear this as Ted and Tony talk further about the details, they've basically given the public a black box, which is sort of a trust us argument. They're not answering AE's questions. They're not responding point by point to AE's arguments. And that's a process violation of the Data Quality Act. They're not doing procedurally what the Act requires. And that may be an independent basis for getting a court order requiring NIST to comply. But you also have the substantive problem that if NIST weren't hiding behind a black box and were responding point by point, they would either have to concede AE's position or they would have to resort to using explicitly what they have done implicitly, which is use data that's not reliable, not accurate, that is biased, not transparent, not reproducible. So to make a long story short, I think architects and engineers and the requesters are well positioned, if need be, to bring a lawsuit. We're hopeful that the appeal officer at NIST will actually do the right thing here. It's pretty clear that the lower level NIST folks did not. We're not giving up on that. I'm not giving up on that. But the Administrative Procedures Act provides a mechanism, even though the Data Quality Act does not explicitly provide a mechanism to sue. The Administrative Procedures Act does. We call it the APA for short. And citizens can sue a government official or an agency that takes an action that is arbitrary and capricious or that is not in accordance with law and get an order requiring corrective action from the agency. So we're preparing for the worst, which is to do that. And Ted or Tony or Richard, if you have questions for me, I'm happy to answer them, but I'll stop there and let you guys proceed. I know you have a lot to say.
Thanks, Mick. I think you covered the essentials really well. And thank you for all your work on this to help make it what it is. I also wanted to, before I move on further, I want to thank many of the people that helped out in putting this request together. There were about 10 or 12 engineers and scientists and other researchers who were part of this and contributed a lot. So I've got the list in front of me so I don't forget anybody. Roland Engel, our board member, civil engineer, Kamal Obeid, Tony Zambodi, who's here with us, Chris Sarnes, David Cole, Niels Harrett, Stephen Jones, David Chandler, Ron Brookman, and Andre Rousseau. So thank you all for the feedback and the input that you provided into this request as well. And Tony, well, before you jump in, Tony, what you're looking at here is a slide that lists the 8 items of information that we highlighted in the request. The first 5 items fall under NIST computer simulations. And the first 4 of those, as Tony is going to talk about, have to do with the initiating failure that NIST claims initiated the progressive collapse of the building. And then there's a 5th item there, NIST global collapse analyses, which I'm going to cover. And then there's part 2 of the request, the latter 3 items there, seismogram data, eyewitness and audio evidence of explosions, and severely eroded steel from WTC 7. I'll say that I think I'm giving Tony the easier part of the job here because the evidence and the critiques that 8E911 Truth and others have developed over the years, where we are critiquing the NIST's initiating failure, is really strong. And you'll see from the responses that NIST gave to the request that they really have nothing. And on some of these, as Mick mentioned, if it comes to us having to file suit, I think on some of these earlier points, we have a very, very good likelihood of prevailing and actually, hopefully forcing this to go back and actually make good on some of the requests. The latter items are a little bit more, I'm not going to say subjective, but it's a little easier for NIST to just say we disagree. But maybe with the exception of the last item, H, which I'll talk a little bit about. So Tony, I'll move on to the next slide, and you can take it away.
Sure. Can you hear me?
And and can you just start by giving people using this diagram just a kind of a simple explanation of the initiating failure?
Sure. Yeah. No, I was going to go through the slides the way you have them.
Great.
At any rate, I just want to give some background and explain why what's going on here. For a building to come down vertically, the columns have to fail. And in a fire, the columns in a fire on a specific floor of a 47-story building isn't going to cause enough damage to a column because the column has a path, a heat transfer path. And this they even had to admit that the columns didn't get hotter than 300 degrees centigrade. That's not hot enough to, steel doesn't lose any strength by that point, or very little. So another way a column can come down, or buckle, I should say, is if it loses lateral support. Columns are tall, and they have to be supported laterally every so often. So what NIST is saying is that column 79 in the northeast corner of this building lost lateral support, and they say that happened because there was 5 beams framing into the 5 beams that are in red to the right there, the 10.2, framing into this Girder A2001 from one side. It was an eccentric type of framing situation. And Girder A2001 supported with column 79 and column 44 laterally. And of course the floor that sat on it. So at any rate, these 5 beams, they're saying expanded enough to push Girder A2001 off its seat at column 79. And that couldn't happen at column 44 because it was between the flanges of that column. That column was rotated so that the girder went in between its flanges. So they're saying that pushed it and rotated. It was on a seated connection at column 79, and then that caused the girder to fall, and that whole assembly of that northeast corner that you see in red fell down on the next floor down and caused the 5-floor cascade. There's some serious problems with them saying that because you can't get enough expansion, and there's other features that would prevent their hypothesis from actually being a reality. So I guess we could move on from there, Ted, because we're going to explain.
Okay.
We're going to explain. This is a top view of the. You're seeing a section of the column. That's column 79. You see the hash marks on, and you're looking at the top of the girder. And the column is interesting. It's what they call a build-up column. It's a heavy, very heavy I section, and you see that they're 5-inch flanges on that 3-inch web, and then it has 2-inch thick by 26-inch side plates welded to it, so it's built up. And those side plates protrude about little under, about one. Well, it's actually 1.79 inches nominally past the face of the I section. So you see that protrusion there. And the girder is actually oriented to it. Its corner, the corner of that girder is only about 1/8 of an inch. The other corner, that corner there, Ted, the western corner, that corner there is only about 1/8 inch clear of the side plate to the left. Now, that's at room temperature. As soon as this thing heats up at just 200 degrees centigrade, it's a 45-foot long beam. It's going to expand about 1.25 inches. That's 5/8 of an inch. So that puts it 1/2 inch inside the side plate. You can see this sort of model, the side plates here. And in their analysis, it actually got stuck in their preliminary analysis. You see it. They don't have it going past that side plate that you see on the upper left, on the right side view. In the left side view, it's at nominal. It hasn't expanded yet. In the right side view, it's expanded, and it's stuck behind that side plate. And that side plate is 2 inches thick, and it's welded along the whole column. There's not a chance that the beam would buckle before that side plate ever ripped off of that column. So they don't address this, even though they show a figure like that. And this is what the University of Alaska at Fairbanks did in their analysis. They show here that the girder certainly, it's heated. This is a stress analysis with heating the beams in the girder, and the column stays a lot cooler. And anyway, you see the girder gets trapped. It goes up against the flange, the face of the column, and it gets caught behind that side plate. That's exactly what would happen. So there's not a chance that that girder could be pushed off its seat. And what this says here is, I'm going to just read the highlighted part. The full-scale model had detailed connection models that are consistent with the fabrication shop drawings as shown in figures 821 and 1115 of the World Trade Center 7 report. The girder A2001 in column 79 connection locates the bolts on a seated connection attached to the exterior edges of the column 79 side plates. The girder acts at a slight angle. They're just telling you what the connection is. They're not giving any answer to the question on why they did not see that the girder would be stopped by the side plate, and when it's obvious in their figure. So on the left is NIST figure 821, and you can see the side plates don't protrude very much. In the left-hand figure, the right side of that, you see a top-down view. And I showed you a realistic 2-scale drawing at first, and they stick out 2 inches. They're 26-inch long side plates. It looks here like they have it sticking out a 1/2 inch, and they have the girder sitting back a significantly more greater distance, at least when you just view it scale-wise, than the actual girder is, or how the actual distance the girder is from the column itself. So Ted, on the right side, I don't know what exactly that was there, but
it's similar. It's similar. I think it's showing it more from a plan view. It's also showing it from a plan view, and
what that's showing is the top and bottom clips.
Top and bottom, yeah.
The bottom bolts in the top clip.
Yeah.
So the section A of the request for correction was about the side plate issue, and we're saying that all this is doing is making general assertions about the validity of their model, and they don't discuss the behavior of the girder at elevated temperatures. It's going to expand. They said it was at 500 degrees. And bear in
Yeah.
mind that there's proof that girder had to get hot. You can't
Yes.
have beams which are connected to the girder and in very close proximity to it getting hot, so they expand and push the girder without the girder getting hot. It's right next to it. You can see they're connected. So if the beams get hot, the girder's got to get hot. If the girder gets hot, it's going to push itself towards the columns, and it's going to be up against the flange of the column at 500 degrees. And it can't get around that 2-inch side protrusion of the side plate.
One thing I want to highlight, which is kind of stated in the second bullet point there, Tony, is that throughout the request, what we also said was, okay, if you maintain your findings, if you maintain your position, then you need to include more information, analysis calculations, or figures that are actually explaining how the girder could move past the side plate. Because in their preliminary analysis, as we showed, the girder gets trapped behind the side plate, but in the larger scale analysis, somehow the girder moves past the side plate.
Well, they don't even talk about it. They just
no, exactly. They don't talk about it. They just assert that it happened.
They just assert that it happened, and it's like saying something wasn't there that was certainly there.
Yeah. So the backup request in each of these points is to provide more information if they stand by their position, which they just completely ignored that aspect of the request.
Justification for their position, right?
Yeah, and they're not amending the report to include more information, which they would need to comply with the.
It's not even more. They never gave a justification for it to begin with. So we're asking for it, and they're not providing it. And then, unfortunately, you have to come to the conclusion that they can't. Okay, this is solid engineering. This is not spin.
So, Tony and Ted, could I insert myself just for a minute? So, looking at this from a lawyer's point of view, and I know there are more examples you have to give of this, but the law may defer, and judges may defer to some extent, to agency expertise in a lawsuit if the agency exercises its professional judgment and its discretion and offers a detailed opinion and a basis for it. What we have here, though, is the agency failing to even offer a response to rebut your technical points. And so here there's nothing substantive in terms of an agency technical opinion for the court to defer to.
Yeah, this
so I just want to point that out.
Unfortunately, we're being given and I don't even like to say this. We're being given garbage. This is not what they have no basis. There is no chance it can get past that side plate. That girder has to get hot. If those beams are hot, it's going to go against the column. It's going to run up against that 2-inch protrusion of the side plate, and it's not going to be able to go any more than 3 inches.
Yep.
And that's
let's talk about a few of the other points.
Right. Now, in addition, there's other things. The side plate is just the first of several reasons this can't possibly happen. So there's multiple avenues, multiple obstacles to what they're trying to say. And by the way, the loss of lateral support has to happen for the columns, any of the columns to buckle. This is the most has the greatest potential, the most potential out of any connection in that building, and this can't happen. So if this can't happen, none of those connections could have failed and caused the columns to buckle. So there's serious problems with a whole natural collapse scenario.
Tony, do you want to talk about beam K3004?
Right. So now and you're going to have to move past this, Ted. Beam 3004. No, don't yet. Just let me look at that other. Beam 3004 is going to control this because as I said earlier, girder A2001 is between the flanges of column 44, so it can only rotate there, up at column 44, Ted, on the north. It's between the flanges of it, so it can't be pushed laterally, except to go against the flange, and then it has stopped, and it can rotate. So those 5 beams there that are pushing on the girder would want to rotate it, but beam K3004 is a limiting factor. It's 52 feet long, and at 600 degrees or so, it's going to expand around 5.5 inches, a little bit under that, actually, in that expansion. So you can go to the next slide, Ted. So in the NIST report, they said a girder was considered to have lost vertical support when its web was no longer supported by the bearing seat. The bearing seat at column 79, that's the seat that the girder sat on, the seat came off the column, was 11 inches wide. Thus, when the girder end at column 79 had been pushed laterally at least 5.5 inches, bear in mind, that's about the maximum that beam could expand. It was no longer supported by the bearing seat. However, when the drawings were released, 3.5 years after the NIST report, which came out in late in November of 2008, the final report, in early 2012, an engineer by the name of Ron Brookman got them to release a large number of the drawings. And it was noticed in an assembly drawing showing column 79 and girder A2001 and the seat, its seated connection, that the seat was 12 inches wide. Well, that makes a big difference because 5.5 inches isn't going to get the web of the girder past the edge of the seat. And so that was brought up to them, and they came back and said that they transposed the lateral and longitudinal or axial distance that the girder would have to fall, but they didn't explain how they could get 6.25. And here's a chart that shows, and this is a very well done chart that shows there's a net expansion, because when the beams get hot, they're going to sag as well as expand, and they'll shorten due to the sagging. So there's a net expansion. And you can see here we have 600 degrees, which is what they said they were at, and it's a little under 5.4 inches. So a 12-inch wide seat, you can never get there. So it would have to be pushed somewhere about over 6.25 inches, and even more than that if you consider the radius between the web. Go back to that earlier, to the table set. At 654 degrees, you only get 5.728 inches. And the reason that's significant is that's the maximum, because after that, the sagging overtakes it, and shortening due to sagging overtakes the expansion. And any temperature higher than that, it's actually gets shorter. The net expansion is less. So they can never get there with these beams expanding. They can never push that girder off its seat that way. But they still want to maintain that it happened, and they just they never determined how they could get any more than that 5.5 inches they initially said. And it's very suspicious. They said the seat was 11 inches wide when it was actually 12. The drawing shows it is 12. Why would you put 11 inches in the report? I think it's self-explanatory, because they could only get 5.5 inches of expansion. Okay, so that's the thermal expansion of beam K3004. And
they avoid giving a specific value for the expansion.
Why don't you explain their response here?
Yeah, I mean, the gist of it is that they avoid actually giving a value for how far that beam expanded or could expand. They simply just don't address any of the analysis in the request.
Well, we've done that for them, and they can't, and they don't confirm or deny. They don't try to refute any of it, and it's absolutely true, correct. Right,
so I think this one takes the prize, but go for it, Tony.
Right. So in addition to that, the fact that the seat was too wide and the beam couldn't expand enough, and it would be stuck behind the side plate to begin with and can never get there, the girder also had web stiffeners on it, partial height web stiffeners they call them. They're half the height of the beam or the web. Now, these are critical because, and this shows this is a solid model. And let me just explain, give me a chance to explain this. These stiffeners are because the girder seat, the orange plate there is what they call a support plate. That's under the seat. So that's supporting the girder's web by 2 inches. So they put these stiffeners on because the web could do what they call cripple or buckle, and it gives it more area for support. But they also, in addition to supporting the web, they stiffen the flange. And for some reason, I think we can guess why, they were left off. Because the claim is that this girder is pushed to where its web is beyond the seat, and the web is taking the load, and the flange is thinner, much thinner. And this is the University of Alaska analysis. Keep going. Stay back with the other Ted, if you will. What they're saying is this was pushed off, and then this left these stiffeners off. Can you go, Ted, to this
Mm-hmm. I mean, this is their,
I want to see the NIST view showing the stiffeners aren't there.
Right.
That's one, and then figure 821 I'd like to see too. I want to show the people that the stiffeners aren't there in this view.
Yeah, I'm going to have to go back for that 1 sec.
Right.
No, did I pass it?
No, I think there
we go. There we go.
Okay, on the left, that's figure 821 from the NIST report. You can see there's no stiffeners there. They're not there. They didn't use them in the model. Now, occasionally engineers leave things out that aren't germane to the analysis. These are very germane because they would stiffen that flange by 80 times. It's 80 times stronger. Anybody that ever took a 12-inch ruler when they were a kid in grade school and tried to bend it when it was flat, it's fairly easy, like a diving board. Turn it 90 degrees and try to bend it where it's like 1 inch or 1.25 inches deep. Even though it's thinner, you can't bend it. And that's what stiffness does. That's what depth, that's what the web in a beam does. Okay, you can't bend it. The deeper that web, the harder it is to bend. It gives it much more bending resistance. Well, those stiffeners, if you can go back to the solid model, Ted. No, you got to go. There you go. Those stiffeners make that flange 80 times stronger in bending. And this said, without the stiffeners, it failed. It was 2 times too weak. All right, so with the stiffeners, it would be 40 times stronger than it needed to be. And this is an analysis by the University of Alaska Fairbanks where they increased the expansion of the beam artificially to get the web. The web is the center of the girder or the beam to get that off the edge of the seat. You can see Ted showing there, and you can see the stress is fairly low. It's not going to fail, and the column is removed so you can see it because you're looking from the back of the column here.
Yeah, and the idea is that this thing would just kind of continue to fold leftwards if there were no stiffeners there. It would just kind of bend over and fold and cripple.
The flange would have curled up. It would have bent up, and the girder would have fallen. But because of these 18-inch high stiffeners, that could not possibly happen. So this is just another thing that could not happen. There's multiples of things that can't happen, like we've already shown.
And we should be very clear about what NIST's reason is for leaving out those, because they acknowledge they leave out the stiffeners, and the reason is
they've admitted it.
Preposterous.
It is preposterous. The reasoning is that they're for web crippling, but there was no web crippling, so they left them off, and that the web didn't cripple in the preliminary analysis. That's sort of like, I was trying to think of an analogy, and I think this works. It would be like testing the wheels of your car in your driveway by taking the lug nuts off and seeing if the wheels would fall off. Well, of course they wouldn't if the car's static and you have a balanced load. But then leave them off when you go driving and see if those wheels don't come off. And that's sort of what they did. It's in that direction. Okay.
Well, and also what's also crazy is that the reason that it didn't have the opportunity to fail is because the girder was trapped on the side plate, which goes back to the issue number 1.
It's a convoluted thing. Issue number 1 was stuck behind, and that's why the things are in the order they are here. And then even if and then we go in stages. If somehow got past side plate, which it couldn't, it can't be moved far enough by the beam. Even if it could be moved far enough by the beam, the stiffeners would stop the flange from curling up, and the assembly wouldn't come down because it would still be strong enough to stay on its seat. So here's 3 things. It's a whole series that show it can't happen, it can't happen, it can't happen. And when you get that kind of argument, it's a real argument. And all they're doing in opposition to that argument is say, no, we don't agree. We don't agree. Well, it's silly on its face. Unfortunately, we're dealing with something that's silly on its face. And it's just bureaucratic inertia that's stopping this.
Yeah. And I want to like read what's at the bottom of this to make it as clear as possible. The web stiffener was not needed to prevent flange buckling in the 16-story ANSYS analysis. That's the larger scale analysis. When the flange buckling must occur for the girder to walk off when it's pushed 6.25 inches. So they're saying that the structural feature was not needed to prevent the failure that actually occurs.
Happened.
That they actually say happened.
Right.
and we know from the UAF analysis and from basic engineering analysis that the stiffener would prevent the buckling.
Right.
So we've just highlighting it there, what their response was. Tony, I think we should move on from this one. This one's very complicated. And we
can just say something about it. You can't break through the next floor down. And you can do an analysis, and that's in the UAF report. And this shows you can do a natural frequency analysis, which was done, and you can determine the spring stiffness of that assembly and how much it would deflect and what the impact load would be. And the impact load is about 10% of what's needed to break through the next floor down. So even that can happen. So all four of these situations can happen. And one piggybacks on top of another, on top of another, on top of another. They can't get there. It's like having multiple doors to get through that can't, are just not going to let you. They're trying to get a much bigger thing through a much smaller hole, and it's impossible.
Yeah. I'm going to take like 2 minutes to talk about the global collapse analyses and NIST response to that. So the global collapse analysis is where NIST talks about once this initiating failure occurred, you had a chain reaction of other structural failures. Column 79 buckles, which column 79 is that key column we were talking about. That buckles, and then the adjacent columns buckle, and the penthouse starts to come down. And so this is their global collapse analysis showing that happening. And then it ends right there. And so as you can start to see, by this point, which is not actually very far in terms of time into the collapse, the building is severely deformed. And we'll get a little bit more into that now in these coming slides. NIST claim here is that the global collapse analyses match the observed behavior reasonably well. The global collapse analysis confirmed the leading collapse hypothesis. So they use this global collapse analysis to say our hypothesis is correct. The animation looks like the real thing, when in fact it doesn't whatsoever. And so that's the claim that we make in section E of the request. Contrary to NIST assertion, NIST global collapse analyses do not match the observed behavior reasonably well and do not confirm NIST leading collapse hypothesis. And we focused on, what we're making the case is that their model fails to match most of the observed behavior, and that it predicts fundamentally different structural behavior from what you actually see in the video. So in the video, you have a lack of, almost total lack of deformation. You have very strong symmetry, and you have free fall, as well as a sudden transition to free fall. These are two figures that are important in the NIST report that show the position of the building at 5 seconds and 7.5 seconds after the east penthouse had begun to collapse. And this is the building. This is the position of the building. This image right here is overlapping the two previous images that you saw of the building. And what it's showing you is that at 5 seconds after the east penthouse collapse initiation and 7.5 seconds after, the upper corners of the building have not moved. And 7.5 seconds after is allegedly 6 seconds, is 0.6 seconds after the point at which NIST says global collapse initiated. So 0.6 seconds after global collapse supposedly initiates, you get a little bit of a dip in the middle of the building, which we'll get to a little bit later. And
let's see why that's important, Ted, because they're trying to show it wasn't in free fall.
Right, but yeah, so we'll get there. But the key here is very simple. You're looking at a building that has not deformed whatsoever after collapse is already initiated, and it's not deformed at all prior to it. This is NIST model. We have here overlaid where the model is at the moment that NIST says the global collapse initiated, which is a little bit earlier in their model. It's at 6.3 seconds instead of 6.9. And as you can see, there's already a lot of deformation. They only show us this angle, perhaps because they don't want to show us how much deformation there is on that southeastern side of the building. And NIST actually says in their FAQs, and they repeated it in their response to the request, only in the later stages of the animation after the initiation of global collapse do the upper exterior wall deformations from the NIST analysis differ from the video images. Well, this is at the moment of
That's at the beginning.
Global collapse initiation. So it's a flat out false statement, and they repeated it in the response to the request. Here's a comparison at 5 seconds. Here's a comparison at 7.5 seconds. So this is like the upper edges of the upper corners, the west and east corner of the building have not even moved yet.
In the real video, they have it.
In the real video, and over on the right is what we have in the NIST model at the exact same point in time.
Right.
And this is where the NIST model cuts off. At this point, the upper corners have begun to move, but in this model, you have severe deformation, et cetera. I'm going to move along a little bit. There's also the directionality. Here we demonstrate that in the NIST model, it's actually tipping. It's tipping to the south, whereas in NIST's own words, part of it began to tilt to the north, and it comes down nearly vertically. The western corner, it comes down nearly vertically. Well, we don't see that here. It's tipping to the south. And just showing that again, this is on the left, we have where it is at 8.3 seconds, roughly. That's roughly where it is here. This is 4 seconds later, and the building is still symmetrical. Imagine if you allowed what's going on in this model, to continue for 4 more seconds. The building would probably be halfway to the ground, but having tipped over. And that's why they cut off their model at that point, because it's tipping.
Right. Well, in real life, it did ultimately tip it. It was like,
yeah, a little bit, but I mean,
halfway down by that point. Yeah.
Yeah. Unfortunately, there's so much detail here that we're not going to be able to get through. But we can maybe post these slides so that people can have a look at them and learn more, and it's sort of a guide to understanding what is so horribly wrong with this.
Well, you can also say they admitted to free fall. They were forced to admit to the free fall because it was a publicly measurable thing by David Chandler, but they didn't address the implications of it. If you have free fall, you can't have free fall and be deforming, providing energy for any other purpose. All of the energy has to be going in, becoming kinetic. So if you're deforming things and things like that in a crushing action, you can't be in free fall. So free fall means nothing is opposing. So something's wrong with saying it's deforming things to collapse the building.
Yeah, real briefly, NIST tries to paint the picture that it took some time to build up to free fall. There was this 1.75 second stage 1 where the building was at slow descent, and this is their depiction of that. When you actually measure different points across the building at the corners and in the middle, you see that at all 3 points, you see that there was no movement of the corners which is what was shown in NIST's own figure here. And then there's a little bit of movement of the middle of the building, which is kind of what you get a sense of from this image. And then simultaneously, all 3 points go into free fall at the exact same moment. So it really is a sudden transition to free fall, which makes it easier for NIST to claim that their model somehow matches the actual behavior, but really it was a sudden transition to free fall.
Well, what they do is just they arbitrarily start the collapse earlier so that to try to show it had that 1.75 seconds, but in reality it wasn't collapsing for most of that 1.75 seconds.
No, and David Chandler measured it kind of. I think these are the best measurements we have to date that show there was a little bit of movement in the middle, no movement at the corners, and then it all goes into free fall at the same time.
Right. Across the entire building. And it's
across the entire building. Right. So the big question is, and there might be an obvious answer to this for a lot of folks, how can the lack of deformation, the symmetry, and the sudden transition to actual free fall be achieved? And that's what the UAF analysis shows us. You can get the east penthouse to fall without having any deformation of the rest of the building if the columns below the east penthouse are failed high up in the building, that will cause the east penthouse to fall, as we saw in the video, without deforming and causing to tilt the rest of the building.
Right.
Or minimally.
The columns were largely intact for most of their height.
Yeah. And this is the global collapse analysis in the UAF study, which shows, again, the symmetry, the free fall, etc. I think that's really, unfortunately, all we have time to cover. There's 3 other points, but I'm gonna skip ahead. We will make this available so people can review it. One thing just to highlight here in the last point, though, NIST's response to central claim of Section H. This is the last section of the request. Despite the discovery of severe erosion in several beams from the World Trade Center, NIST neglected to perform tests to determine the cause of the erosion in one such beam recovered from WTC 7, and then falsely stated that no identifiable steel was recovered from WTC 7. NIST's response is basically to say we cannot confirm with 100% certainty that beam was from Building 7. Now, all of the professors, researchers who studied this beam, everyone who has studied this believes that the beam came from Building 7. There's a lot of documentation to suggest that. And so this is one point, along with the earlier points, where we expect to be hitting this very hard in the appeal.
I just say one thing real quick. It could be the type of steel that was used in Building 7 as opposed to the towers, and the shape. The shape of that beam may not have been anything they used in the towers, and that's why people knew it was from World Trade Center 7.
There's a very, it's almost, we have to study this.
Physical proof.
No, it's all, I can't say with 100% certainty, but based on what I've read so far, we know 100% that steel wasn't from the towers. So if it wasn't from Building 7, it would be from Building 6 or 5, etc. But I think you could say with, I think there's a sense with 99% certainty this is from Building 7. And the second point here, which is, we will be raising in the appeal, is not being able to confirm with 100% certainty that it was from Building 7 is not a rational basis not to examine it. If you examine that steel and you run tests and you perform other experiments and determine that thermite or some form of thermite is the only thing that could account for that phenomena, well, it tells you that phenomena was maybe possibly responsible for bringing that building down.
What you got to say is what the phenomenon was. It was vaporized. Part of the steel was vaporized, right? It was melted.
Yes.
Melted and actually vaporized, right? It has tremendous heat to do that.
So as Mick mentioned, the appeal is due 2 weeks from now, Sunday, September 27th. And this is the gentleman at NIST who will be reviewing the appeal. Mick, do you want to say anything to sort of wrap this up from a administrative and legal standpoint?
Well, what I'm impressed with from what you presented as a lawyer is that there's several points in this response, putting their procedural failures aside, where they just give illogical responses, non-responses, black box sort of trust us responses. I don't really expect those to work with a judge, with a court on close analysis. This whole thing about the stiffeners, and we didn't have to use them in the second model because we didn't put them in the first model and we didn't have any walk off of the beam in the first model. That only works as what they call a conservative assumption if you don't change anything else in your model the second time you go through it. But if you use a different kind of model the second time, it doesn't matter what your first model showed. As a matter of simple logic, you can't trust that the assumptions in the first model, that the outcome from the assumptions in the first model work for the second one. So you have what we call a disingenuous argument. It doesn't hold up under simple logical analysis. So I think you got valid scientific arguments, but you got some basic logical mistakes.
Yeah, and I'll say, I think with the appeal, I think our job is to make it as difficult as possible for him to stand by what the other folks who did this have written in the response, but and to make it as easy as possible, to find some way to really make it easy for him to go back and say, no, you guys really have to run this again. And then if that doesn't have it, have made it so simple in the appeal that it's incredibly easy for a judge to understand. That's really the job that we're trying to accomplish in the appeal.
Well, yeah, they haven't answered. That's the point. They have not answered.
And we do have a question from the audience for Mick also. Again, what is the legal maximum consequence for officials at NIST if they continue to ignore this? Can anyone hold their feet to the fire?
Well, that's a good question. Under the Data Quality Act, you're not going to get a punishment per se. You're going to get corrective action. You may get an injunction requiring NIST to go back and do it right, which could be huge. I mean, if they go back and do this study right, the consequences are going to be huge to tell the truth about why Building 7 collapsed. If the questioner, if the audience member who asked the question is wondering, can you really get accountability for folks who did this knowingly wrong? That's either a criminal matter, and there is a crime involved. I'm not suggesting at the moment crimes were committed or were not committed, but if you make a false statement in any matter before a federal agency, it's a crime, even if you work for a federal agency. You've also got the Federal False Claims Act, and you've got the perjury statutes, obstruction of justice. There are things that could be looked at. So folks can be punished depending on the severity of the misconduct.
Gotcha. And the process that you guys are in now, another viewer asks, could it ever involve direct talks with NIST? Interesting question.
It could. I mean, you could get, a judge may ask for those face-to-face discussions before the matter is litigated, like a settlement discussion.
And for Ted, are there any people who wrote the official NIST report who are involved in answering the request for correction?
They have not been as explicit as they should be about who prepared the request and who was involved. There were 4 names copied at the bottom of the request, which is publicly available. They're the various staff all the way up to the chief of the engineering laboratory, but in the headquarters for the engineering laboratory. I think that group of people, none of them worked on the NIST report and the NIST investigation. I think they clearly, at a minimum, consulted with people who did work on the investigation, who are still there or who are still, in communication with NIST. And we have asked NIST to tell us who else was involved in the preparing the response, because there's a specific rule in the guidelines that anybody who was involved in preparing the response cannot be involved in reviewing the appeal. So what is the definition of involved? Does that mean if they had a conversation with Shyam Sundar that Shyam Sundar was involved, that's the NIST lead investigator, and can not be involved in the appeal? You would, to some extent, you would maybe imagine or even hope that the person who will review the appeal may be able to consult with people to find out why'd you do it this way? But so I don't know, but yeah, going back to the original question, yeah, I mean, we have a sense that it was these 4 people, but there were probably lots of others who were involved.
Okay.
But nobody officially who worked on the investigation.
Gotcha. Any final quick statements? We've got to move on. We're about 20 minutes late now because of our earlier glitch. Not your guys' fault. Any other wrap-up statements?
If I could, one last observation from a lawyer's point of view. This idea of sending the draft initial decision to a higher level in Department of Commerce, and then when there's an appeal of that decision, having the appeal decided by our lower level in NIST is problematic, because you got what's supposed to be an independent official deciding something they know their superiors have already stamped their approval on, which is a bit of a biasing factor, which I've actually never seen happen, I don't think.
Yeah, what Mick is referring to, in case people listening don't know, in some definitely don't know, is that NIST sent their initial decision to the Department of Commerce to review before they send it to us, and that was responsible for the 2-week delay in them sending it to us. And so it does seem irregular that they send it to the Department of Commerce first. It seems to be, as Mick said, it presents a problem then when you have somebody up higher up at NIST reviewing the appeal when the Department of Commerce has already been involved in reviewing the initial decision.
Gotcha. Thanks, gentlemen. An awesome presentation. Really appreciate it. Clarifies a lot of questions there, and great questions too from our audience. So we'll catch up with you guys soon. And thanks again so much for all the hard work you've all done on this project. We're going to persevere and make it happen. Take care.
Thank you.
Thank you, Richard.
All right.
Pleasure.
Take care.
Go on, that guys.